Hello, and welcome back to me, Silas Freeling, explaining the second FRQ in this 3 FRQ project for Mr. Pavico's physics class. This question, the FRQ I will be talking about, is from 2019 AP Physics 1. It is 12 points with a suggested time of 25 minutes. So, in order to go about solving this problem, I will first read the problem aloud to you. However, I will not answer any of the questions. Then I will explain all of the physics required to answer the questions, and then I will go about applying those skills that I have taught you into solving the actual problem, putting the ideas to the paper and applying it in order to get a good score and to get the correct answer. I was thinking that with the basics I already covered in the previous video, I wouldn't need to cover them again. However, this problem still has a lot of information I have not covered and a lot of things I need to talk about that are beyond just the basics of that first one with the ball being dropped, as this one has a bit more complicated of a setup, I would say. It requires some initial knowledge. So I will start by reading the situation. I will read the problem. I can give you a quick sketch of the situation to make it more clear, and then I will go about the things we need to learn, and then I will explain them. So let me read the question. There is a diagram. I will show you a bigger drawing afterward. Okay, so this problem explores how relative masses of two blocks affect the acceleration of the blocks. Block A of mass ma rests on a horizontal tabletop. There is negligible friction between block A and the tabletop. Block B of mass B hangs from a light string that runs over a pulley and attaches to block A, as shown above. The pulley has negligible mass and spins with negligible friction about its axis. The blocks are released from rest. Okay, so right now I'm going to show you a diagram that I have added, and I will give it to you. Okay, so here is a blown up drawing of the situation. As you can see, you have block A on the table and block B hanging from a pulley, and it is off the table being pushed down by gravity. So let's read question A. There are 2 parts, although really more like 4 parts because each part has 2 questions. The first part of question A is, suppose the mass of block A is greater than the mass of block B. Estimate the magnitude of acceleration of the blocks after release. Briefly explain your reasoning without deriving or using equations. 2 is, hold on. 2 is, now suppose the mass of block A is much less than the mass of block B. Estimate the magnitude of the acceleration of the blocks after the release. And then you need to explain your reasoning without deriving an equation. Question B is, now suppose neither block's mass is much greater than the other, but they are not necessarily equal. The dots below represent block A and block B. Dots are provided as indicated by the labels. On each dot, draw and label the forces, not components, exerted on the block after release. Represent each force by a distinct arrow starting on and ending from the dot. And then C was, derive an equation for the acceleration of the blocks after release in terms of mass A, mass B, and physical constants as appropriate. And then D is to consider the scenario from part A 2, where the mass of block A is less than the mass of block B. Does your equation for the acceleration of the blocks from part C agree with your reasoning? And then you need to briefly explain your reasoning by addressing why, according to the equation, the acceleration becomes or approaches a certain value ma when is much less than mb. When ma is much less than mb. Question E is, while the blocks are accelerating, the tension in the vertical proportion of the string is T. That's a variable. Next, the pulley of the negligible mass is replaced with the second pulley whose mass is not negligible. When the blocks are accelerating in this scenario, the tension in the vertical position of the string is T2. How do the two tensions compare to each other? And then to briefly explain your reasoning. Okay, so in order to go about solving these problems, there are some concepts that I am going to need to explain to you. I have written them all down as a brief synopsis, and then I will go in depth into each one. So first, you need to know about tension as a force. You need to know about how to set up free body diagrams. That's really important, so I might as well review that. You needed to talk about the Newton's equations and how to use the Newton's equations with free body diagrams to cancel out terms and to solve in terms of desired terms. Next, you need to look at the sum of forces in a desired direction on an object. You need to be able to calculate the F net. And then I would like to teach you about the concept of friction or explain how friction works. In this problem, there is no friction on the table, but I feel like it would be important if you could learn what would happen if there was friction and how that would also affect it. I should mention that if you are not asleep at this point, that is a very good scale, because I don't know who would be able to sit through this boring stuff. I mean, yeah. Anyway, first I want to briefly mention how pulleys work. Say and what tension is. Tension is essentially just a force exerted on an object that can be caused by the pulling of a string, which is then exerting a force on that object. So tension is just a force that involves something being pulled by a string. A pulley, right? Say you have a rope with a pulley going across, and you have a mass and another mass. The tension is going to be equal for both masses, despite the pulley being there. The pulley just breaks it up, but the tension is equal on both sides, so it's the same tension pulling this mass down as the one that's pushing this mass up or keeping this mass in place. Or having a upward pull on that mass, even if it isn't keeping it in place. So the first thing I want to review really quickly is free body diagrams, as they are important. I did already talk about them. However, they're very important, so I might as well mention how you could use them to solve the problem. First things first, when you do not know what to do, break everything up into a free body diagram. Break up both masses into a free body diagram, and that will let you visualize how you can use Newton's equations to solve for any of the desired variables. So I'm going to start with that real quick here. We have mass 1 and mass 2. I'll use this example, but you could use any example. Mass 1 is going to experience a tension force across the table. Mass 2 is going to have a tension force back up, as mass 1 is still applying a tension force to mass 2, but it's also going to be experiencing its force due to gravity down, so mg. It is important to remember when you're making a free body diagram that, I don't know if I mentioned this in the previous one, a longer arrow means a greater force. So if you want to keep two things equal, they should be the same length. And if you want to mention that one thing is longer, it should be a lot longer than the other one on the free body diagram, or that a force is stronger, it should be a lot longer on the free body diagram. So I've drawn a quick free body diagram of mass 1 and mass 2 in this example, and this is really important because it will lead into my next step, which is showing you how to use Newton's equations in order to solve for a variable. So here is the free body diagrams of both of them. Here's mass 1, here's mass 2. Mass 1 is being pulled off the table with the tension T, and mass 2 is being pulled down with its weight due to gravity. However, it is also being pulled up with an equal tension T. As you can think about it, the mass of the first one is still pulling on the mass, or the mass of the one on the table is still pulling on the mass of the other table. It is applying a force, and it is applying an acceleration. Now I'm going to talk about the most crucial part of this second FRQ, and that is learning about how to look at the sum of forces on an object in a certain direction, and learning how you can apply that 2 Newton's equations in order to be able to eliminate variables. You see, right now in the example, we have so many variables. We have tension, mg, acceleration, we have mass 1 and mass 2, and automatically the question is asking for us to represent acceleration in a way that doesn't have tension. So automatically you need to know how to cancel out and eliminate some of these variables. And the way you do that is through looking at Newton's equations and through getting a sum of the forces on objects, because if you do that, you can end up setting variables equal to other variables, and you can substitute, you can use elimination, you can use substitution or elimination mainly. Both of them should work. Okay, so the crucial thing to remember, the thing that's going to come up is F equals ma. Force equals mass times acceleration. This is Newton's crucial principle that is going to come up a lot in this problem. Now I'm going to talk about looking at the sum of forces on an object, right? F equals ma, right? If you want to look at the sum of the forces on an object, it is important to choose one direction that is one of the reference axes you set. So that means that if you have a vector that is not completely aligned with one of the reference axes, you should break it up so that it matches those reference axes. Break it up into 2 components and then look at the force net in either direction or potentially in both directions. So in order to find the force net, as it is much easier to visualize with these free body diagrams, you look at F, sum of F net in a certain direction, and you look at all the force acting on it. So as you can see in my free body diagram, this has tension acting on it. This tension is the force, as it is causing an acceleration upward, and it has a mass, and this thing has a mass, and this mg is a force, as we know, because there is a constant acceleration downward due to gravity, and this has a mass. So neither of those values are 0, and therefore you are going to get that a force does apply. As you can see in the second free body diagram, I am actually missing 2 things that I should include in the second free body diagram. I should include the mass due to gravity, or the force of the mass times gravity, or weight, as that is still part of the force on mass 1. However, it is canceled out by the equal normal force. So this is what mass 1 should look like. And remember, these are canceling out. So then we have only a tension on mass 1. So say you want to look at the sum of 2 forces. I'm going to start with this one because it's simpler. What is a direction that has multiple forces? Well, the y direction. So I can look at the sum of the forces in the y direction. And remember, the sum of forces in the y direction also equals the ma, right? So we know that the F net in y direction of the first one is that t minus mg equals ma. This is because they're in opposite directions, so you have to subtract the vectors. One's going along in a certain direction, the other is going in another, so you have to subtract them, versus if they were both going in the same, you would have to add them. So we have t minus mg equals ma. Now this is pretty obvious. You can tell just by looking at something at rest on a table. It is not accelerating up or down, and since it is not accelerating up and down, that acceleration is 0. There is no force done on it, as would be quite obvious. It's not moving. Its forces cancel out, right? It's not being pushed down through the table. It's not going up. The normal force is canceling out the gravity and causing no net force. You can tell there is no net force, as I said, because it was not accelerating. So you have t minus mg equals m times 0. M times 0 is just 0, so you have t minus mg equals 0, and that is the sum of the F net, or the sum of forces. And then if you do substitution to get t on its own, you can very clearly see that t equals m1g. Not t, that n. My bad. This is n the whole time. I don't know why I was calling it t, right? The normal force is canceling out the gravity. So you have n minus m g equals 0, so you have n equals mg. Now, as I was saying, I mentioned that earlier, that's pretty straightforward, but we just proved that the normal force is in fact equal to the mass due to gravity. As we know, it is not accelerating. It must have a net force of 0, which means if it has a net force downward of a certain thing, it has to have an equal net force. Or if it has a force downward of a certain thing, it has to have an equal upward force to keep it at 0 and to keep it from moving. This is not the case with the second example. If we want to break down the tension now this time, last time I was breaking down the normal force and the weight, if that wasn't clear. Now we're breaking down on the second one, we're breaking down the tension and the mass due to gravity. Now, we're going to assume, since there is no friction, which I'll get into later, that this system is going to move downward. Yeah. Now, since in this example we have a frictionless surface, which is kind of weird and not always the case, I don't necessarily know if there would actually be a T pointing up from that second mass, because the first mass would just be sliding along. So I think that the forces on it are just mg in this example, but right now I will look at an example where, say, there is a tension and say there is a mass due to gravity, implying that there would potentially be a frictional force. So say in this example that I have created here, I guess it's not entirely matching the one given, but I will explain the one given. Say in this example where we have a tension and an mg in the second direction, in the y direction, that you can look at the sum of the forces and you can say F net equals mg minus tension equals ma. It is going to be falling down, right, as it is going to be pushed down by gravity, and so we can say that it is accelerating and it does have an ma value. If it was not accelerating, if it's not accelerating, then you know that the tension equals the mg, as I said earlier, because the ma equals 0, so you have tension minus mg minus tension equals 0, so tension equals mg. But say it is accelerating, then you can say mg minus tension equals ma. Okay, so actually, you may want to forget what I was saying earlier. So actually, there would be a tension on the second mass, on the hanging mass, whether or not there was a frictional force. Either way, there would be a tension force. So that means that this problem is still representative of the practice problem, in which case we have mg minus t equals ma. If it's not accelerating downward at all, then you know that the mg equals the tension. However, as long as it is accelerating, you know that the mg minus the tension equals the ma, as the F equals ma and the F net also equals the acceleration. So from here we can say that tension equals mg minus ma, or we could solve in terms of mg and say that mg equals tension plus ma. However, I find it the simplest to use the elimination method. So right here I'm going to say you have a hypothetical example of a mass on a table. Actually, let's do one on a ramp, with a pulley on a ramp, because that is going to be more unique than the situation previously. Say you have an incline of theta, right, and you have a pulley, and you have an overhanging mass of m2 and then mass of m1, right? A little scenario I created right here. So I'm going to start by drawing the free body diagrams on all of them. This is obviously assuming a frictionless surface, and for the second one, so for the second one, there's a tension pulling it up, right, which is equal to the tension pulling it down, and a mass 2 times gravity. And we can automatically look at the sum of forces. The F net equals tension m2g minus tension equals ma. I'm keeping it as m2g minus tension because it is accelerating downward, which means that I'm saying that downward acceleration is positive, and it's minus m2g, and it's minus tension because the tension is decreasing the downward acceleration or increasing the upward acceleration. If it would make more sense with upward acceleration being positive, you could say that it was negative m2g plus t equals ma, but I'm leaving it as m2g minus t equals ma. for the sum of forces on 1, right, I changed it to be a ramp. So now there's actually not going to be a normal force that completely cancels out the regular force. So this will make it more interesting. Let's draw a free body diagram for mass 1. I will show you it in a minute, but there's going to be the mg. There's going to be a mg cos theta canceling out the normal force. Mg cos theta. And there's going to be the force pulling it down, which is mg sine theta. And there's going to be the tension that's pulling it up. Now we're only going to look at the forces in the x direction for this one. However, if you want to solve for friction, you need to look for normal force. I will talk about that later, and in that case, it would be really important to break that one up, as you can get the n in terms of the other things when you have it equal to, in magnitude, mg cos theta. So this is what the free body diagram would look like for this one and for the second one. And so we already set up the F net for the second one, where m2g minus t equals ma, right? In this first one, we have a different m net. We have the force pushing it down and the force pushing it up the ramp, right? And obviously, in this scenario, I'm going to say that mass 2 is heavier, and therefore mass 2 is going to be pushing it down the ramp. So we can say that the sum of F net on 1 equals tension minus mg sine theta equals m1a, and this one equals m2a. So now we have two equations, both of them with tension, and tension is usually something we want to get rid of. It is usually not one of the terms they allow you to keep things in the AP test, and it can also be left out in terms to simplify the equation, and you could get the acceleration. In order for it to be accelerating upward, I might just say the tension has to be greater than the mg sine theta, which is pulling it back down, which means you can get tension on its own for the second one, which means that the m2g minus m2a would have to be greater than the mg sine theta, m1 being m1g, and the other one would be m2, but that is sort of a rabbit hole I'm not going to go down. So I have these two equations I set up here with the F nets, and they're both in a certain direction. One of them's in the y direction, one of them's in the x direction. However, that does not matter because it's both the same tension, so I can cancel out that tension, and I'm left in terms of m2g, m1g, and sine theta, and m1, m2 I already said, an a. And the a is going to be the same for both of them. They're going to be both accelerating at the same rate. So we can actually get rid of that too. You have to be careful. You can't cancel out masses because they're different masses. There's an m1 and an m2, but we can cancel out these using the elimination method, which is sort of just adding the two equations, right? Because I have this negative t in the first one and this positive t in the second one. So if I do add the two equations, if I do add the two F nets, I get m2g minus t plus t minus mg sine theta. So those t's cancel out and you just get m2g minus m1g sine theta equals, and then you can you just can add the other side too, m2a plus m1a, and you can factor out this m actually from, you can factor out the a from this side of the equation, and you can actually factor out the g from this side of the equation if you want to. So you can have g m2 minus m1 sine theta equals a times m2 plus m1. Factoring out this a allows us to divide both sides by m2, m1, and you actually get what the acceleration equals in this scenario, which can also be applied to the FRQ I will talk about. This scenario can be applied to any frictionless surface with tension. It's basically the same procedure for like any frictionless thing where you're trying to figure out what the force equals. If you have two different masses, two different things where you can make free body diagrams for, you can look at the rates, you can look at the variables, you can set them in terms of other variables, or you can cancel out variables. You can set a variable in the second one in the terms of the first one and plug it back in, and boom, you've gotten rid of a variable. In this case, I'm doing the elimination method, and I got a on its own, and you can see a equals g times m2 minus m1 sine theta over m2 plus m1. So I have this acceleration right here for this ramp example that I made up. This is different from the table example. We can get into some more spicy issues now, or more spicy problems with friction and this concept of friction that I am about to go into. So I'm going to give a quick overview of friction, and then I'm going to go back to the ramp problem if there was friction, and I can also go back to the table problem if there is friction. I might just do the ramp, and then as I'm going over the FRQ, I'll talk about, hey, what would happen if there was friction. So friction is a force, right? And it exists in the real world, although often it is, not often, but sometimes it is neglected in physics problems. But it is the force of the ground or of any surface pushing back on an object as it is moving in a certain direction. Friction is always opposite of a force applied. It is never going to be in the same direction of a force applied. If a force applied switches, the direction of friction will also switch. You can get scenarios where friction is in the same direction as the force due to gravity, though, however. So it is important to remember that it can be in the same direction as the force of gravity. This is actually going to come up in my ramp example because it's being pushed up a ramp, which means part of its gravity vector, its force due to gravity vector, is going to be broken down, and it is going to be the same way as friction, as they are both opposite the force applied, which is up that way. So there are two kinds of friction: static friction and kinetic friction. Friction always pushes with an equal force to where equal or less force with what you apply. So it could either be applying an equal force or less of a force. Now this makes sense because you're never going to push an object or apply a force to an object on a surface and all of a sudden it's going to start pushing your hand back, right? There's never going to be a frictional force great enough that it is going to actually be greater than the force you applied, and it's going to do more work than the force you are applying. It will either do equal work or the same work, unless it's going along with distance. But I'm not really sure. Okay, so yeah, so there are two types of friction: kinetic friction and static friction. Static friction is always stronger than kinetic friction. Kinetic friction is when you are pushing something and it is moving, and static friction is the friction something pushes back when it is not moving. When it is not moving. So basically, right, you're going to be pushing something, and it is going to be giving an equal frictional force of static friction. However, it reaches a maximum static friction point force that depends on multiple things. It depends on its normal force, which depends on how heavy it is, how much force due to gravity is acting down on it, or if there's another force pushing down on it. And it also depends on how much contact it is making with the surface, because that also is what attributes to normal force. So it turns out that normal force and friction are really related, and this is what is going to allow us to solve for friction as often we can break down the normal force, or we can use the normal force when we're looking at an F net or at a force net in a free body diagram. As you can see, there was a normal force and there was a tension. And that canceled out with the mg cosine theta in the ramp problem. So friction is related to normal force. And you might be asking how? Well, friction equals a frictional constant called mu times the normal force. It is proportional to the normal force. As the normal force increases, the friction increases. However, it is equal to a mu times the normal force. Yeah. And that mu is just going to depend, that value of mu is just going to depend on, it's going to depend on how heavy that object is. It's going to depend on the surface. A surface is generally going to have mu changing mu, I think. So I don't know if it really depends on the mass, although the frictional force does, but that's only because the normal force depends on the mass, because as the mass increases, the normal force increases. So basically the friction coefficient, or mu, just depends on the type of material or the type of ground that the object is traveling on. Yeah, so you have this equation F equals mu n, and this mu could either be mu static or mu kinetic, and the value for mu changes. Like the same object, the same surface is going to have a different static mu value than a kinetic mu value. They're going to be different. However, the equation is the same if friction is static or kinetic. They're both mu n. It's just that one is mu s or mu static n, and one is mu k n. So F equals mu k, and I have written them both down right here. So now that we need to have everything we need to know about friction, we know the equation and everything, I would like to go back to my ramp problem, and this time say the ramp has friction. So you have these two masses on a ramp. Let me draw them out for a second time. Let me do that a bit bigger. You have these two ramps, a bit bigger, I said. You have these two ramps. So you have these two masses. Mass 2 is dangling, and mass 1 is on the ramp, except this time the ramp has friction. I'm going to indicate it has friction by drawing shading on the ramp. So this means that when a force is applied on this first mass, there is going to be a frictional force backwards, and it is either going to be kinetic or static if it is moving or not. So let's look at a scenario in which case it would be moving, and you can actually determine what the mass required or what the force required would be in order for it to move. You see, if there is a mass on a ramp, or if there's a mass on a table, or even a ramp, if there's a mass on a table and there's no friction and there is a dangling mass, it's always going to go this way because it has no force to keep it from going that way, no counteracting force. And on a ramp, if there's a mass and a dangling mass, it's either going to fall down the ramp because it's force due to gravity in that direction. It's mg sine theta is either going to be stronger than this force dangling down, or it's going to be less, and this is going to be pushing it down, and this is going to go this way. However, if there is friction, there is actually an opportunity in both cases where neither thing is going to move, where both are going to remain still, and you will be able to see that. Although first, let's just look at our example, and let's say, okay, it's going to be moving upward in this, and the mass 2 is going to be moving down, which would imply that the mass 2 would apply a tension force that is greater than the mg of the first one, the mg cosine theta of the first one plus the friction of the first one, as you'd be able to see using an F net or a force net, which I will show. Okay, so I'm going to start by breaking up both of them into free body diagrams. The free body diagram of mass 2 is the same as before, right? There's no frictional force acting on it because it's not making contact with any ground. There's going to be a tensional force up, which is equal to, it isn't equal to, but it is in the opposite direction of a force of mg down. And this is going to be an F net equation, a force net equation, where mg minus tension equals ma. Now, however, we have a different scenario when you break up M1, mass 1. I'm going to break it up into all its components, including, I'm going to show the normal force too, because this is going to be able to visualize our friction. It is going to allow us to put it in something else, in another term, as friction itself. And we can actually get normal force in its own term. Friction itself often isn't going to be a term they want you to leave it in, because usually they want you to leave it in. It's the same with tension. They want you to leave it in constants. Those constants can be mu, can be theta, and they want you to leave it in terms of the masses. So I'm going to break this M1 down into its corresponding forces. There's the gravity, which I'm going to break down into the mg cosine theta on the ramp, and the mg sine theta. The normal force stays up. It's perpendicular to the ramp, and it is parallel to the mg cosine theta. And then there's this tension force being applied upward, and there is also, at this time, this frictional force being applied this way as well. So your free body diagram should look a little something like this, that squiggly F. I know it's kind of hard to see because it is like going to be reversed, but that squiggly F is the friction. So now we can look at the F net in that side, right? And I'm going to start by looking at it in the direction which I defined as the horizontal one, which is going to be parallel to the ramp. And I'm going to look at the sum of force net equals tension minus mg sine theta, right? That's a force, minus the frictional force is also a force. It's also minus frictional force equals ma. And it is going to be accelerating in this scenario. So yeah, equals ma. It's not going to equal 0. It's going to equal ma. However, we can simplify it more. What are we going to break this friction down into? We're going to break it down into mu n. Friction equals mu n. Now, n is not a term we want to leave it in, though, but we can simplify it even more, right? As you can see, looking in this vertical direction, you can see that the sum of forces in the vertical direction is F net mg cosine theta minus n is going to actually equal 0 because there's not going to be an acceleration up or down. Say you have an object sitting on a ramp. I don't know where my magically 8-ball prop. Right now, here it is. If you have an object sitting on a ramp, right, it's not going to move up off the ramp or down below the ramp at all. And that is because the force upward of the normal force is going to be directly equal to and canceling out the force of the weight due to gravity sideways. So, we can say that mg cosine theta minus n equals 0. We can add n to both sides and you have n equals mg cosine theta. We can now plug that back in for m in the friction equation, so you have n equals mu mg cosine theta. We can plug that back into the original and we get tension minus mg sine theta minus what we found to be friction, which is mu mg cos theta, minus mu mg cos theta equals m1a. Now I'm going to use the same process I did earlier, and I'm going to get rid of these tensions because I have a positive tension and a negative tension in both equations. I'm going to add them up. I'm going to add the F nets, and I'm going to get the tensions cancel out. I'm going to get m2g minus m1g sine theta minus mu m2g cosine theta equals m2a plus m1a. I'm going to factor out an g from this side and an m from the other side, as all the terms on the left side have a g and all the terms on the right side have an a. So m2 minus m1 sine theta minus mu m2 m1 minus mu m1 cos theta equals a m2 plus m1. I will solve for them and I will get the acceleration. The acceleration is going to be equal to the g times m2 minus m1 sine theta minus mu m1 cosine theta all over m2 minus m1. This is actually going to be true for any scenario. And so you can shift the masses and it's going to tell you the acceleration. So now you'll know, hey, how heavy does this bottom mass need to be for it to actually be moving down, and for it not to be moving up when the ramp is actually when the first mass is actually heavy enough, or that mass is actually light enough that the mg sine theta and the friction actually when it's going down is going to be pulling in the opposite direction, but the mg is actually greater than the tension and the friction going upwards. So now I want to look and I want to tell you for what values it is going to be going up, and for what values you can tell it's going to be going down for the masses, and for what values you can tell it's going to be staying still. Okay, so if we look at the free body diagram and we look at the F net, you can tell it's going to be moving up when the tension is greater than the frictional force, which we called mu mg cosine theta, plus mg sine theta. Now we can get the frictional force on its own, or the tension force on its own, by looking at the free body diagram too, and you can see that tension equals mg minus ma, m2g minus m2a. So m2g minus m2a. I might as well factor out the m2. m2g minus a is greater than mu m1g cos theta plus mu plus mg m1g sine theta. So that is the scenario where it's going to be going up. It's going to be going down when the mg sine theta is greater than the tension and the frictional forces. In this case, the frictional force is going up. So it's going to be mu mg cos theta plus the tension, which we can also call m2 g minus a. So that is cool. So for the first equation I just set up, where if we do a little manipulating, the first equation, t is greater than mu mg cos theta plus mg sine theta, and you can turn t into m2 g minus a. You can manipulate the equation and you can find out that in order for it to be moving up the ramp, in order for it to be pulled up the ramp, the mass 2 has to be greater than the mass 1 times mu g cos theta plus g sine theta, all divided by g minus a. Now you can do similar approaches for the other ones, and you should see that there is actually a wide variety of what the second mass can be. I don't have any numbers, and I don't want to get some weird crazy numbers, but you should see that there's a wide variety of masses where the mass 2 could be, where it actually wouldn't change, right? The static friction would not break and it would not be moving up or down. So if you find out the other way, you'll find out a value light enough where it's going to slide the other way. I can do that real quick just to give you a better case or a better understanding. Okay, so it is going to slide the other way if the second mass is less than mass 1g sine theta minus mu mass 1g cosine theta all over g minus a. So this gives you a wide range. It's important to remember from what I've been saying here that basically with friction, even on the table example, it's not always going to slide down. The first mass, however, without friction, no matter how light the second mass is going to be, it should be pushed at a very slow rate, even if it's small, or it should always be moving, because there is never going to be a force to counteract that, right? Its force due to gravity is directly down. Its normal force is directly up, so you can't break those down. And yeah, so it is always going to slide without friction, but with friction on the table, there will be some values where it won't slide, and you can calculate if it will or if it won't by setting up one of these inequalities that I just set up. So now I believe you have all the needed information to revisit that FRQ. Well, that's where my jacket was. I've actually been looking for this bad boy. I want to wear it to school, and it's been on my chair the whole time. So yeah, so now we have enough information to revisit those FRQs. So the first question, right, it's just giving a sort of synopsis of the surroundings, and then it asks in question A, suppose that the mass of block A is much greater than the mass of block B. Estimate the magnitude of the acceleration of the blocks after release. Well, block A is the mass on the table, and block B is the hanging mass, so mass A is going to be much greater than the mass of the block on the table than the block B. However, there is no frictional force, as I was saying, which means it is going to be a slight acceleration for both of them. One of them is going to be going downward, block B, and one of them is going to be to the sideways, block A, but block A will eventually fall off the table. It will be moving downward, as there will be no force to counteract that force that block B, no matter how small it is still providing a tensional force, and there will be no other force to counteract that force on block A. There is no opposite force, right? There is the normal force and there is the force due to gravity, but as I said, those are completely in the opposite axes. You can't break them down at all into any vectors in the same axes. So it is going to move. It is going to move slightly. B is going to fall slightly because the tension is going to be almost as great as its mass due to gravity, right? It's going to give the equal tension that it gets, so it's going to give a small tension compared to block B, but compared to block A, but it's going to be actually a relatively large tension for its size because block A is so much bigger than it. So yeah, it's going to be a small thing. It says to explain your reasoning after. I believe that that's what I just did. The answer is going to accelerate down a small amount. There's going to be a small force, a small acceleration, and then block A is also going to have a small acceleration this way. And then I just explained the answer because there's no forces to cancel out A being pushed, and because it is going to be a light tension force no matter how light, there's nothing to cancel it out, so it will continue to move. Now it's saying suppose block A is much less mass than block B, so block B is bigger. In this case, it is also going to still accelerate across the table. Remember, in a friction, the surface is always going to accelerate. However, it is going to accelerate much faster, at a much faster rate, as the tensional force pulling it down is going to be much greater. And as well as that, the mass of block B is going to be much greater in comparison, which means the force pushing down on block B is going to be greater in comparison. So you're going to have this greater tension force. Tension force is going to be caused by it's going to be a certain value of the mg, and with a greater mg, it's going to be a certain greater value of that original tension, and there's going to be a greater force that is pushing it down across the table. So now it asks you to draw a free body diagram. I will explain that in a second. So basically now it's asking you to draw a free body diagram when the masses are around the same. Right, the mass shouldn't really matter. It's still going to cause an acceleration on block A. Block A is going to have a tensional force that way, nothing to cancel it out that way, and it's going to have the normal force equal to the mg. And then block B is going to have an m2g and a normal force, and that normal force, and not normal force, that tension is going to be less. It is going to accelerate downward. So it should look like what I just drew right here, where you have this is block A, and you have this is block B. Yeah. So part C is asking you to derive an equation for the acceleration, which we can use using the force nets I've been talking about. I used one with the ramp, however I can show you the example with the table finally. You have this table, right? We can do a free body diagram of the hanging mass, and then a free body diagram of the stationary mass. And on the hanging mass, there's going to be a tension, which is going to be, and an mg, which is going to be mg minus tension, m2g minus tension equals ma. And on the first mass, tension equals ma, as there's no other force to combat it. The tension equals the m1a. So now we can just use the substitution method, or the elimination method. So yeah, I'm going to use the elimination method. I'm going to add them, and I'm going to get mg equals, that should be m2g equals m2a plus m1a. Let's factor out the a. m2g equals m2a plus m1a. Factor out the a. m2g equals a times m2 plus m1. Divide by m2 plus m1. Divide by m2 plus m1. A equals m2g over m2 plus m1. And that is the derived equation. That is correct. Now it is asking you to consider the scenario from part A2, where the block of mass A is much less than the block mass of B. Does your equation for the acceleration agree with this? So we said that the acceleration would be a lot greater when the mass of block B is comparatively bigger. Block B was represented by mass 2 in this equation. And does that make sense here? And the answer is yes, it is going to make sense, because you have m2g over m2 plus m1. Now, when the acceleration is bigger, that means that either the numerator is bigger, the numerator, or the denominator is smaller. So if m1 is really tiny, you have this m2 times 9.8. As long as m1 is smaller than 9.8, I think it would have to be in kilograms. The acceleration would be less. So if it is a really tiny mass, then the acceleration would actually be greater, and say that m2 was really large, then it would have like this really large number. Yeah, so the acceleration would be greater, so that does agree with our reasoning. This also shows that the more you increase the mass 1, the slower it'll accelerate, which makes sense. Or, yeah, that makes sense. Mass 2 doesn't really matter as much because it's on the numerator and denominator, so when you increase it, it's going to increase on the numerator and denominator. But when you increase or decrease mass 1, decreasing mass 1 is going to increase the acceleration, and increasing mass 1 is going to decrease the acceleration, and that does check out with our answers. Also, the more you increase mass 2, the more the thing will accelerate as well, because as mass 2 gets so much bigger than mass 1, that small little addition you are doing of mass 1, forget what I said earlier, multiplying by g, multiplying by almost 10 is always going to, as you get to numbers getting bigger to infinity, you are going to see that top number being so much more than this m2 minus this m1, or plus this m1, which as long as m2 is going to infinity, m1 is going to look very tiny compared to it. So as m2 gets bigger, the acceleration does get smaller. It's asking, briefly explain your reasoning why, according to the equation, the acceleration becomes a certain value m1 when ma is much less than mb. So ma is the block A. When m1 is much less than mb, it's going to, when m1 goes to 0, right, the acceleration is just going to be m2g over m2. So the m2's cancel out, and the acceleration is just going to be g, which is pretty neat. And it makes sense when you think about it, right? If something is falling and it has no mass attached, it's going to be going to g. It's going to be falling at a rate of g, and the more mass you attach to it, the slower it is going to be falling. So this is actually true with what I was saying earlier. The bigger mass 2 gets comparatively to mass 1 is basically just the same as mass 1 going to 0, right? Because you're going to have this m2 times g that is almost going to perfectly cancel out, right? As this m2 gets bigger, m2 is becoming almost identical to m2 plus m1. So as it gets bigger, it gets closer and closer to being able to cancel out with m2 plus m1, and it's going to cancel out almost perfectly and more as it gets bigger. So it is going to go to g when you increase mass 2 or when you decrease mass 1, because increasing mass 2, when you make the ratio so much bigger, that mass 1 is barely noticeable, and that is going to be almost equal to, and mass 2 over mass 2 plus mass 1 is going to get closer and closer to 1 as that mass 2 gets greater.